Hi friends, good morning to all. Welcome to an academy. So this is the new online learning platform. All of you know that last 8 months we are facing so many problems in outside. That most serious thing is COVID-19. Because of that, most of the students are unable to going to college and they are unable to attend the college classes. To solve that problem, they started an academy, started a online learning platform. Welcome to an academy. So an academy is the India's largest learning platform. Myself, G Venkatrao. I have 16 plus years of teaching experience. So far, I mentored more than 60,000 students for GATE. At present, I am pursuing PhD in JNTU Kakinada in VLSI domain. That is a brief about myself. So first we check how to install an Academy Learning app in your Play Store. Just go to Play Store, type an Academy Learning app in that and click on install button. Then it will install an Academy Learning app in your device. Open that. In that you get different modules. These are the some of the top educators in an academy. You observed or not, almost all are ex-IAS officers, IIT toppers. Okay, and they are from different departments. Here you can get few more. So sir is from civil engineering, general studies and aptitude, instrumentation engineering, civil engineering, mathematics, mechanical engineering. Okay, faculty from different departments. Now here is the for GATE 2023 electrical branch. These are the new stream started. This batch is started in English language and it is starting from 18th January. Today onwards it is going to start. Okay, to subscribe this, use my code VRAW10. This is my code VRAW10. By using this code, if you subscribe this, you get 10% discount. And this is the another branch. So same for EC students also. From today onwards, new English batch is started. For this, this is for GATE 2022. Okay, this is the Spark batch. And use my code VRAW10 for this also. You get 10% discount by using my subscription code. So this is for 2023 ECE people. It is also starting from same today itself. So use the same my code VRAW10 to get most discount. And this is for again Spark batch for GATE 2022 for electrical people. Okay, so these are the top educators: Ankit sir, Venkat Reddy sir, Shankar sir, Trinath Reddy sir, Ajay Gupta sir. These are the top educators from an academy. So these are the most senior faculty members. Okay, use their services, gain the knowledge and get success in your life. So these are the different departments they are providing for GATE: ECE, CSE and IT, civil engineering, electrical, mechanical, general aptitude, instrumentation engineering, production and industrial, chemical engineering, mathematics engineering. So they are providing chemical engineering also. Okay, so this is very helpful for the chemical students. And here there are two subscriptions. One is a plus subscription, the next one is iconic subscription. One is Plus subscription. Second one is Iconic subscription. In Plus subscription, these are the 1 month cost. This is for 3 months, for 6 months. This one. Now this is a Iconic subscription. For this cost is for 24 months it is available for 54,000, and for 12 months it is 40,500. During subscription, use my code VROW10. By using this subscription, you get the 10% discount. So during plus subscription and Iconic subscription, you get following facilities. So you get the classes from India's best educators in both the case, and live classes that to interact also. Structured courses and PDFs. They will provide well structured course to you, and proper PDF material of that respective subject they will provide, and they will provide live tests as well as quizzes also. These quizzes and tests are very useful to you. And here personal coaching is plays an important role here. Personalized test analysis, study planner. They prepare study material also. Okay, here they are going to take the personal attention based on your strength and weakness. They will prepare a plan, and if you follow that plan point to point, definitely you will get success in that. This plan is prepared by well senior topmost educators. Okay, so I wish you all the best to one and all. Now we are going to start this session on this. So these are the plans just before what we discussed, and plus plan, Iconic plan. This is for first plus plan for 12 months. Okay, and this is Iconic plan for 12 months. This is the cost, and for 24 months they are charging 74,000. Now today we are going to discuss about what is electronic device, and what is the classification of electronic devices and semiconductors also. First of all, see here our subject now is electronic devices and circuits. Most of you are calling it as electronic devices and circuits. So we are calling the subject EDC fine and electronic devices and circuits, but very few people know the meaning of what is electronic, what is electronic device, and what is electronic circuit. First, let me clarify that. First, electronics. How can you define electronics? What we understand from electronics. See, electronics is nothing but a study of movement of an electron in a semiconductor. Study of movement of electron in a semiconductor. Study of movement of electron in a semiconductor. That is electronics. Next one is electronic device. It is a device which is made by a semiconductor. Which is a device made by a semiconductor. A device made by a semiconductor. Now, here I have electronic device. It should made by semiconductor. then only you can set it as an electronic device. Next, electronic circuit. It is a circuit. Let us take a circuit having multiple components in it like this. Now, in this circuit, at least one component should be electronic device. Then only you can call that circuit is electronic circuit. Then only you can call it as an electronic circuit. Once again I am repeating these things are electronics. It is the study of movement of electron in a semiconductor. You have to highlight this, semiconductor. Early days the definition was different. Early days the definition for electronics is it is the study of movement of electron in three different states: solids, liquids and gases. Now everything is semiconductor. Once explosion taken place in a semiconductor, now everything they are going to be concentrating completely on semiconductors. Now the new definition for electronics is it is the study of movement of electron in a semiconductor. Okay, after that, electronic device. Electronic device, a device which is made by semiconductor. Made by semiconductor. See, here also we have semiconductor because this device was made by semiconductor. Next, electronic circuit. It is a circuit with at least one electronic device. One electronic device. See, once it is electronic device, it should be made by semiconductor. See, in electronics we have semiconductor. In electronic device you have a term semiconductor. In electronic circuit you have a semiconductor. So if you know much about electronics, first you should know about semiconductor. Semiconductor. Okay, if you gain much information, much knowledge on semiconductor, then it is very easy to you to understand the working principle and controlling way of electronic device. Okay, that's why first I am going to concentrating much on semiconductor. Now I am going to first classifying the materials based on the conductivity. Now first one is conductors, and second category of materials is semiconductors. Third category is insulators. Conductors, semiconductors and insulators. Now how can we define a conductor? All of you know that a material which allows free flow of charge carriers. A material which allows a free flow. Is semiconductor is a crystalline material. It is in the form of crystal. Okay, now how can we define a semiconductor? See, it is defined as semiconductor behaves like either conductor nor insulator based on external conditions. Once again I am repeating, sir. Semiconductor behaves like either conductor nor insulator based on external conditions. Now what is this meaning of external conditions? See, here the external condition means this is, let us take your semiconductor. To increasing its conductivity, what you are doing, how its conductivity of the semiconductor is increasing, varying, that depends on this external condition. Okay, later we go to that. Now first I am going to this point to point semiconductor. So it behaves like a conductor or insulator. At a time it behaves like only one, either conductor or insulator. At a time it behaves like only one, either conductor or insulator. In some books they mention semiconductor is a partial conductor. Partial conductor in this sense, this is the meaning of that. Either it behaves like a conductor or insulator, only one at a time, either conductor or insulator. Its a conduction or its conductivity is partial compared to the conductor. That means its conductivity is not up to the level of a regular conductor. For increasing conductivity, we are doing something. What we are doing and we discuss about that one later. Okay, and here default external condition is temperature. So that means, see here, conductivity of a semiconductor is a function of basically three parameters: temperature, intensity of light, and though adding impurity. Okay, I given this term based on this view, based on this temperature, intensity of light, or impurity. Okay, now default condition is temperature. If it is other than temperature, they will specify. Okay, now at low temperatures, your semiconductor behaves like an insulator, and at high temperature, semiconductor behaves like a conductor. Now low temperature means generally we take it as at 0 Kelvin, and high temperature in this sense we consider it as room temperature 300 Kelvin. So at low temperatures at 0 Kelvin, semiconductor behaves like an insulator, and at room temperature semiconductor behaves like a conductor. Okay, I will show this how it is insulator and why it is conductor at 300 Kelvin. I will show that later. Now the common semiconductor, the general semiconductors what we are using is silicon and germanium. These two belongs to fourth group elements. Okay, silicon and germanium. In these two, mostly we are using default semiconductor is silicon. Silicon is the default semiconductor. Now I am going to classification of semiconductors. So far we know what is semiconductor, which behaves like either conductor nor insulator based on external conditions, or you can use the term based on external temperature. Okay, so at low temperature semiconductor behaves like an insulator, and at high temperature semiconductor behaves like a conductor. Okay, now I am going to classification of semiconductors. In this, first classification is elemental and compound semiconductors. Elemental and compound semiconductors. Next one is direct and indirect semiconductors. And the last one is intrinsic and extrinsic semiconductors. Okay, now first I am going to elemental and compound semiconductors. See this elemental semiconductor. Means, let us take a semiconducting crystal. It is a semiconductor crystal. We know that everything is composed by atoms. These are the atoms in a semiconductor what you taken. Let us, I am saying it is a silicon semiconductor. The meaning of this one is, whatever the atoms here we have, all the atoms are similar type. This is silicon atom, this is silicon atom, this is silicon atom. All the atoms are silicon atoms. All the atoms are silicon atoms. Okay, that is elemental semiconductor. So a semiconductor which is composed by similar type of atoms is called elemental semiconductor. Example, silicon and germanium. Okay, next, compound semiconductors. See, let us, I am taking LED. If you take LED, the material what we are using for LED is gallium phosphide is the material we are using for LED. This gallium is not a semiconductor and phosphide also not a semiconductor. Same way, you take gallium arsenide. It is used in laser. Arsenide. See, it is not a semiconductor. It is not a semiconductor. In this, no silicon and no germanium. Okay, now this is using in the designing of LED, light emitting diode. Our LED is a electronic device. Electronic device. Once it is electronic device, the material what you are using for the designing of this should be semiconductor. Should be semiconductor. Okay, now here it is composed by two different type of atoms, gallium and phosphide. Similarly, it is also composed by gallium and arsenide, indium phosphide, zinc sulfate. Okay, like that you can combine. And the four most important and first compound semiconductor is silicon germanium. Silicon germanium is the first compound semiconductor. Silicon germanium is the first compound semiconductor. In this we have silicon atoms as well as germanium atoms. They combined both. That is first compound semiconductor. Okay. Now you may ask one thing. Sir, already we have elemental semiconductors, silicon and germanium, and by using those we are doing wonders. Then what is the necessity to go for this? You get that necessity in next second category. We have direct and indirect semiconductors. There you get that importance, and I give some more importance of that. That is, these compound semiconductors are used for high speed devices. High speed devices. Okay, and the devices where emission and absorption of light is required. The devices where we need emission of light and absorption of light. Okay, there we are using this. See, this gallium arsenide is used in laser, gallium phosphide is used in LED and gun diode, and zinc sulfate, it is used in it is a fluorescent material used in television screens. And these materials, cadmium, silurium, tin, silurium, tellurium, used in light detectors. Okay, so this is the first category of semiconductors, elemental and compound semiconductors. Most of the students know about only this intrinsic and extrinsic semiconductors. Okay, very few people know about this classification, elemental and compound, direct and indirect, intrinsic and extrinsic, this complete category classification. Okay, so this is the elemental and compound semiconductor. So gallium arsenide also a semiconductor, that is compound semiconductor. For third year and final year people, so you are using studying VLSI, those who are studying VLSI, they know about while comparing the different available technologies in terms of power dissipation, you have different technologies. So this is a delay on x-axis, power dissipation on y-axis. Okay, while comparing the different technologies on the scale, here you get gallium arsenide technology. Okay, gallium arsenide also one of the technology. Okay, now already most of you know about NMOS technology, PMOS technology, CMOS technology. Okay, and BiCMOS technology. This one, next BiCMOS technology. Okay, and bipolar technology. And next level of technology is a gallium arsenide. In future technology is gallium arsenide technology. That means they are going to, our IC is going to be completely designed by gallium arsenide. That is the future coming technology. Okay, so this is about our elemental and compound semiconductors. Next one is I'm going to second category, direct and indirect semiconductors. See, to know about direct and indirect and to understand much about direct and indirect semiconductor, first you should know in detail about energy band diagram of a semiconductor. Energy band diagram of a semiconductor. Now, see how can we draw the energy band diagram of a semiconductor. Before going to that, you should know about atomic structure. Any material you can take in the universe, it is composed by atoms. Composed by atoms. Okay, and this is the way of representing any atom. At center you have nucleus, it is positively charged. Nucleus is positively charged. Next, first orbit, second orbit. This is first orbit, this is second orbit. Okay, and this is the second orbit, and after this there is no orbits, so that's why we called it as outermost orbit. Outermost orbit. Outermost orbit it is. Okay, now electrons are rotating around the nucleus in this orbit. Electrons are rotating around the nucleus in this orbit. Now, why electrons are rotating around this nucleus is serious. Electron is basically negatively charged particle. Nucleus is positively charged. So there is attractive force between this positive and negative. Okay. Due to this attractive force, this electron is if this electron is fall into this nucleus, positive negative both will cancel to each other, then nothing will be there, everything will be collapsed. So electron is there negative, nucleus is positive. Okay, if electron is rotating around the nucleus, surrounding around the nucleus, the attractive force from the nucleus is going to be overcome. Okay, so electron is rotating around of the nucleus to overcome the attractive force from it. Okay, see the best example for that, let us take a glass, or a bowl. Okay, take some water, keep spoon in that, now rotate it. By rotating, after some time you can view the water movement like this. So like this. Now you get the cone shape. Like this. At center nothing will be there, it is a gap. At center nothing is there. See, nothing you get. So water is rotating like this. It is rotating like this. At center you are not getting anything, it's like a cone shape. If you remove the spoon, after some time you observed slowly, initially it is like this, now slowly it is moving like this, finally it is a flat. Initially it is like this, after removing your spoon it is like this, initially like this cone shape. Now slowly it is a cone shape, is slowly disappear like this. Here what happened? Once the water molecules are rotating around the nucleus, they are not attracted by this. Okay, once their speed, that means their movement, their rotating movement, their speed is decreased, this nucleus attracted this electron into this. Now this water molecule fallen into this. Once the water molecules slowly reducing their speed and they are falling into this, that's why whatever the cone initially we have, it is a disappear slowly, finally it became flat. Like this. That is okay. So this is very important, sir. Why electron is rotating, okay, and how to, once it is rotating, okay, on this electron, here we have a nucleus, now here is electron. So just before you said attractive force, to overcome this attractive force, electron is rotating around the nucleus. Fine. With respect to this, electron is facing another issue, that is a repulsive force from adjacent electron which is in the same orbit. Here is one electron, let us take. Here I am taking another electron. Sorry. Here I am taking, this is one electron, and here I am taking another electron. Here I am taking another electron. Now just check this. Between these two electrons, this is negative. Here it is also a negative. Between these two electrons, a repulsive force is there. So to overcome this repulsive force, again electron starts rotating around of its own axis. It is going to be rotating around of its own axis. Okay. See, finally, from this we can conclude one thing. Electron is rotating around the nucleus to overcome the attractive force from the nucleus, and electron is rotating around of its own axis also to overcome the repulsive force from adjacent electrons. Anyway, your electron should be always in movement. Electron should be always in movement. So electron is always in movement with some velocity. Electron is rotating with some velocity. Always it is moving. It is not sitting and it is not standing. It is not fixed at one point. It is rotating continuously. And electron possesses some mass. Now I am adding some constant to this. Now half mv square. This is the kinetic energy of an electron. This is the kinetic energy. So once electron is in movement, it possesses some energy. That is what we are going to learn. Energy. Band diagram. Why we call it is band is, once you are taking our intention is to study about semiconductors. Once you are taking a semiconductor at room temperature of 300 Kelvin, if you take a silicon semiconductor, the number of intrinsic carrier concentration, we call it, number of free electrons here is 1.5 into 10 power 10 per centimeter cube. Per unit centimeter cube of space, this many number of electrons are available. That many number of free charge carriers are available for conduction. Okay. So it is very difficult to represent the energy of each and every electron individually. Because of that, we are going to representing that energy as a band. Okay, and one more. By applying external conditions, that means all of you know that doping, adding impurity to a semiconductor. With respect to doping, energy band diagram is varying. With respect to external biasing, let us I am taking semiconductor and applying some biasing, positive, negative. Due to this biasing, the energy band diagram of the semiconductor is changing. Okay. So based on that energy band diagram, we can identify or we can understand how the carrier movement is changing. From that, once carrier movement is varying and once you have control on the carrier movement, automatically your electronic device is under your control. The intention behind the study of electronics is to maintain a controllable current flow in a electronic device. You can take any electronic device, either PN junction, BJT, FET, MOSFET, okay, photodiode, whatever you can take it. It's not an issue. But our intention in that is to maintain a controllable current flow in that. That is our first motive. To maintain a controllable current flow. That current what is flowing in that should be under your control. Otherwise, that is very dangerous. Already you observed Robo movie. Okay, in that Robo movie, first one, part 1, first half, Robo is under control, everything is positive. Second half, Robo is out of control, everything is a disaster. Okay, so that is a difference. So once you design something, okay, or manufactured something, means that should be under your control. then only you can make positive things by using that one. Okay, so finally we concluded, once you take an electron, it is continuously in movement. Due to that movement, it provides some energy from that movement. Okay, now see, that was we mentioned here. So it is posing some energy. Now here my intention is to understand the energy band diagram of a semiconductor. That is my first intention. Okay, from that knowledge I can go for energy band diagram of a conductors, insulators also. That is a different case. Now first I am taking here silicon. Now silicon, its atomic number is 14. It means 14 electrons present in that. That is the meaning of this. Now the electron configuration for this one is 1s2. Here I am writing this 1s2, 2s2, 2p6, next 3s2, 3p2, 1s2, 2s2, 2p6, 3s2, 3p2. So that was written here, mentioned here. In this first one, it is going to represent the orbit or shell. This is the one in this sense, first shell. This is 2. This 2 represents orbit. Second shell, second orbit. And the last one is 3. That is third shell or outermost orbit. Third shell or outermost shell. Why it is outermost shell? After that there is no shell, no orbit. That's why that is outermost shell. So this number represents orbit number. And power, yes, 1s2 we are calling it. It represents number of electrons present in this shell. In first orbit 2 electrons are present. That 2 are s electrons. So you can represent that by like this, 2 electrons. Similarly, in second shell, 2 s electrons and 6 p electrons. Total 2 plus 6, 8 electrons. So in first orbit you have 2 electrons, second orbit 8 electrons, and third orbit 2 plus 2, 4 electrons. 8 plus 2, 10, plus 4, 14. Total 14 electrons completed. Okay, so now see this silicon atom, first orbit 2 electrons, second orbit 1, 2, 3, 4, 5, 6, 7, 8 electrons, third orbit or outermost orbit 1, 2, 3, 4 electrons. Okay, now every time it is difficult to represent a silicon atom like this. Okay, I want to represent my silicon atom in a simple way. Okay, but it shows me complete information about the silicon. See here my intention, our intention in electronics is just before I mentioned, to maintain a controllable current flow. To maintain a controllable current flow. Okay, how to control? Later we verify. How to get conduction? First, to get a conduction you need charge carriers. And once you have charge carriers, the charge carriers should be in movement. Once charge carriers are in movement, then you get conduction. Now here let us take this electron in first orbit and this electron in second orbit and this electron in third orbit. Which electron you are using for conduction? Electron in first orbit, or electron in second orbit, or electron in third orbit? Which electron you are going to be using for conduction? First of all, now these electrons in the same fashion, these electrons are useful for conduction or not? See, first orbit, it is much close to the nucleus. Now this electron is much attracted by this nucleus. Attractive force on this electron is more compared to remaining orbits, electrons on remaining orbits. Next, attractive force is more on this. Next, attractive force on this electron is less compared to remaining. So that means whatever the electrons rotating around the nucleus, those electrons have some attractive force from nucleus. Okay, so those electrons are under the influence of nucleus. Those electrons are not useful for conduction because they are not moving. Why? Because already they are attracted by that nucleus. They are under the influence of silicon atom, silicon nucleus. So to get a conduction, you need free charge carrier, free electron. But that is not a free electron because that electron is under the influence of silicon atom. Now I want to take this electron out of this orbit. Now we have 3 orbits, 1, 2, 3. Now which electron you want to remove? Now I choose outermost orbit. So always I try to remove the electron from outermost orbit, not inner orbits, because here you observe these 2 orbits are completely filled. Okay, it is very difficult to remove the electron from a completely filled orbit because they are very tightly bonded. Okay, so this orbit is not completely filled, and that too this is outermost orbit. This nucleus having less attractive force on this electron, less attractive force. Okay, this is rotating but less attractive force. So from external side I will provide some external energy. By providing some external energy on this, I will take this electron out of this. Now this electron is not under the influence of silicon atom. This electron is not under the influence of silicon atom. Okay, so this is now your free electron. Okay, here vacant position is taken place. With that vacant position we call it as a hole. Okay, later we discuss about that. Now this is our free electron. This free electron is now useful for conduction. You can use this electron for conduction. Okay, so from these 2 innermost orbits I don't have any business because the electron which is present inside that is not useful to me. Okay, I have some business with only outermost orbit. Okay, I don't want to go inside of that. That's why now onwards I'm not going to representing this, because that means I'm going to simplifying my work. Okay, now onwards I'm going to representing this silicon atom like this. This is the silicon nucleus, and Here is the outermost orbit. Outermost orbit. So electron is rotating around of this. So here electron is rotating. Electron is rotating around of this. Now onwards, I am going to representing silicon atom like this. Now onwards, I am going to representing silicon atom like this. Okay. And this is your valency shell or outermost orbit. So it has 4 valence electrons. 1, 2, 3, 4. 4 valence electrons. So these are the 4 valence electrons. Okay. Now, this is our silicon atom. So far we know how to represent a silicon atom and what is the meaning of that. Okay. Now, if you take a silicon crystal, okay, in that every silicon atom is going to form covalent bond. See, this is going to form a covalent bond. Form a covalent bond with 4 adjacent silicons. This side one silicon, here one silicon, here one silicon. One silicon atom here, here another silicon atom, here another silicon atom, and here another silicon atom. Forming covalent bond with 4 adjacent silicon atoms. Okay. Now, see like this. So this is the silicon atom. It has 4 valence electrons, and this is another silicon atom, 4 valence electrons. This is another 4 valence electrons. Like that, every silicon atom is having 4 valence electrons. Okay. And this is the 2-dimensional representation of a silicon crystal. Okay. And this is a 3-dimensional representation of silicon crystal. 3-dimensional representation. So okay. Now, okay, here see, just before we mentioned, this is a silicon atom, and surrounding of this is the nucleus, and this is the outermost orbit. So here 4 valence electrons we have. These are the 4 valence electrons. Okay. Now, let us, I am giving some numbering to this for my better understanding purpose. 1, 2, 3, 4. And these are the energy levels of 4 electrons. Energy of first electron, energy level of second one, energy of third one E3, and energy of fourth one is E4. Same way, I am taking another silicon atom. Silicon atom. So again here also I have same. One, two, three, 4. So now here my intention is, from the knowledge of energies of individual atoms, I want to deduce the energy band diagram of a complete silicon atom. Energy band diagram of a complete silicon atom. So that is my intention. To get a complete silicon crystal, you need to take plenty of individual silicon atoms, and you have to bring all the atoms close to each other. When those atoms reach the interatomic state, this is one silicon atom. one silicon atom, one silicon atom, one silicon atom, one silicon atom. So between this covalent bonding is there. Okay, like this. Okay, by bringing atoms close to each other, when they reach their standard interatomic distance, they form covalent bond to each other. Then we said silicon crystal is formed. That is my intention. To get that, first I am going to check, once two atoms bringing close to each other, how their energy levels are changing or how their energy levels are varying. That is now I am going to check. See, these are 4 electrons and their energy levels we given like this: E1, E2, E3, E4. You may ask one thing, sir, 4 are similar type of electrons. So once similar type of electrons and all are belongs to same single atom, then they has to pose equal energies. Why they are posing different energies? See, we have quantum numbers, 4 quantum numbers. If you take any 2 electrons in this 4, those 2 electrons are differed by at E4. So these are the different energy levels now here: E1, E2, E3, E4. Now both the atoms are identical. The first atom, what are the properties posed by first atom? Second atom also poses same thing. But here my intention is to form a bonding between these two, covalent bond. That means I want to bring the atoms close to each other. Now that's what I am going to do in here. Now moving this one this side and moving this one this side. Now this is my silicon atom, first one, and this is another silicon atom here what we have. So this is the electron from this one, first electron, and this is the first electron. Both are forming covalent bond to each other. Covalent bond to each other. Electron 1, and here it is also 1. Now the remaining are remaining electrons 2, 3. 2, 3, 4. Similarly, it is here is 2, 3, and 4. Okay, this is orbit, outermost orbit. Now yeah, now say this. Now these two electron 1 here and this electron 1, both are going to forming a covalent bond. We call it covalent bond. After covalent bond, you can't say this electron belongs to this electron belongs to this. You can't say like that. Both the electrons belongs to both the atoms. That's it. That is the meaning of covalent bonding, sharing. Now the way how electron, second electron, third and fourth electrons we represented here, and here no change in their representation because there is no interaction between these electrons with other electrons. Only electron 1 here and electron 1 here, both are interacting. Okay, so that is interacting. That means they are forming covalent bond. That means they are going to forming electronic system. Electronic system they are going to forming. So remaining are unchanged. That's why because of that their energy levels are not changing. Their energy levels are not changing. No change in E2, E3 and E4. Here only these two electrons are interacting to each other. We have Pauli's exclusive principle. According to that Pauli's exclusive principle, in an interacting system, in an interacting system, no two electrons possess same energies. No two electrons possess same energies in an interacting system. See, here is, this is our interacting system. Here both electron 1 are participating in an interaction. Both are interacting to each other. Okay, now their energy levels are splitting. Different. That means both should pose different energies. Let us this is E1 dash and it is E1. It is E1 dash and it is E1 double dash. Okay. Now from this, what we understand from this, initially these two atoms are identical to each other. That means both are separated. Their energy levels are same, equal. When atoms bringing close to each other, their energy levels are different. That means initially same energy, E1. Now once both are interact to each other, it is starts splitting. Initially single energy. Once both are single energy, once both are bringing close to each other, their energy level is splitting. Became two energies. So that is the important point here. We need to draw the energy band diagram of a complete semiconductor. Okay, now finally I am going to concluding this. From this, my conclusion from this is, when atoms are bringing close to each other, the energy levels are splitting. Okay, now here this is the same slide. Individual atoms, individual energies they are posing. Okay, now once bringing close to each other, they are forming covalent bond. Due to this covalent bond, they are interact to each other. According to Pauli's exclusive principle, these two should pose different energies. Okay, now that's why energy level is different, changing. So it is splitting. Energy level is splitting. Okay, now this is the point I'm going to be using here to represent the complete energy band diagram of a semiconductor. Okay, here now I am going to taking n silicon atoms, n number of, it is n means number of silicon atoms, number of silicon atoms. Okay, n number of silicon atoms I am going to taking here. Now all these n number of silicon atoms are initially identical to each other. Okay, identical to each other. That means there is, so far there is no interaction between these n atoms. Okay, I want to bring all these n atoms close to each other and I want to analyze and I want to study how the energy level is changing. Now initially, now I am going to plot this on this. So on y-axis I am going to taking the energy, and on x-axis I am going to taking the interatomic distance. atomic distance. Now in a decreasing, interatomic distance means decreasing. That means I am going to bringing atoms close to each other. Atoms are identical initially, bringing close to each other. That's why interatomic distance is decreasing. This is the, at initial stage, all the atoms are identical to each other, and electron configuration is outermost electron configuration for this silicon is 3s2 3p2. Now let us this is the 3s energy level, 3s energy level, and this is a 3p energy level. Let us okay. Now I am going to bringing atoms close to each other. When try to bring the atoms close to each other, what happens? Just before we observed, their energy levels are splitting. See, its energy level is splitting. It is splitting. Same way, its energy level also splitting. Now here both the energy levels are much. Now again, now it seems to be a single energy band. Here. Okay. Now, so far covalent bond is not formed. Okay, let us assume this is the distance at this point covalent bond is going to form. That means this is the interatomic distance of this silicon. So that means your atoms has to bring much closer. Okay, already you brought those atoms somewhat close, and you need to bring those things much closer. So for that, during that process, again this is going to be splitting again. It is going to be splitting again. Okay, now at this point we have to be concentrate. Here these are filled levels. This is also a filled level. So this is a defined energy level. Silicon atom, you can place 2s electrons and 6 p electrons. See, 2s electrons, 6 p electrons. That means here 6 electrons, in this sense 6 energy levels are defined already. If you have electron, that electron will go and occupy that energy level. Defined energy levels are total 6 in P. If you have one electron, that electron will go and occupy one energy level. But here you have 2 electrons. So 2 electrons will go and occupy 2 energy levels. Remaining 4 energy levels are different. These 2 energy levels are occupied, and the remaining 4 are vacant energy levels. That vacant we discuss after this. Now, here 2s electrons and 6 p electrons from in a single atom, but we have total n silicon atoms. Due to this, 2n energy states are defined, energy levels are defined. Similarly, 6n energy states or energy levels are defined. Defined energy levels. Okay, if you are going to a theater, in that theater nearly 150-200 seating capacity is there. Okay, that is available seating. Okay, now crowd is 50%. That means for a 200, let us take 100 members are attended. Now these 100 people are going and sitting in only 100 seats. That is occupancy. Okay, availability is 200 seats, occupancy is 100 seats. That is the difference. Here also just identify that difference. In a s orbit you can accommodate 2 electrons. That means in s 2 defined energy levels are present. In s. Similarly in p 6 electrons you can accommodate. That means 6 energy levels are defined in P, that means available energy levels. So such type of atoms, here you have N. This is from each atom. Now such type of atoms I am using N. That's why 2N energy states here, 6N energy states here. Now these are energy states, 2N energy states or energy levels, you can call it. States. Here these are same energy states or energy levels. Energy states or energy levels. Now these two are merging here. Both are match. Now 2 plus 6, 8. Total 8N. 8N energy states. Energy states, or you can call it energy levels. No issue. Now this is our standard interatomic distance. At this point, these 8N energy levels are split into two equal halves. These are 4N energy states or 4N energy levels, and these are 4N energy states or energy levels. So 4N plus 4N, total 8N. Now you want to say strictly, this is going to be upper 4N energy levels or energy states. These are lower 4N energy states. Lower 4N energy states. Okay. Now this is about energy levels splitting. Here in silicon atom we have 2 s electrons and 2 p electrons. 2 s electrons and 2 p electrons. Okay, that means total 4 electrons are available from each silicon atom. From each silicon atom, 4 electrons are available. Okay, such type of silicon atoms I have N. Okay, from this N, 4N electrons are available. At 0 Kelvin, these available 4N electrons occupy the lower 4N energy states. Okay, that's why you called at 0 Kelvin conduction band is completely empty and valency band is completely filled. Okay, now I am going to adding another slide, and this is the portion what I am going to highlighting now onwards. This is the region I am going to be highlighting now onwards. Okay. Just 1 minute. Hello, madam. Yes, ma'am. Ma'am, tell me. Yeah, I'm in class. Yeah, I'm in class. Okay. Yeah, it is in live, ma'am. So class is in live session, madam. That's I'm right. Tomorrow we will check off it, ma'am. Tomorrow I will modify this. Please. Now, see here. This is the thing we completed previously. At interatomic distance, you mentioned the levels like this. And like this. These are upper 4n energy states, upper 4n energy states, and these are lower 4n energy states. So I am representing the same thing here in a detailed way. Detail, yeah. So these are lower 4n energy states. These are upper 4n energy states, upper 4n energy states, and there is a energy level which is not defined. This is called energy gap or forbidden energy gap. That means no energy level is defined in between this. Okay, now a little bit, okay, just a moment, I am going back to two-dimensional crystal representation of silicon atom. If you go to that, here is silicon, and this is the way of representing two-dimensional representation of a silicon crystal. Yeah. So here, so this is there's a covalent bond between these successive silicon atoms. So each silicon atom is going to forming covalent bond with 4 adjacent silicon atoms. Forming covalent bond with 4 adjacent silicon atoms. Yeah, these are the 4 valence electrons for this. So for this 4 valence electrons, 4 valence electrons of this, and of this, of this, 4 valence electrons of this silicon atom. Same way for this 4. Yeah. Now here, this is the representation of silicon at 0 Kelvin. Sir, this temperature representation is very important. Okay, this is at 0 Kelvin our silicon representation, and this is the 0 Kelvin energy band diagram representation. Either representing silicon semiconductor like this and like this, both are same, but it is very easy to us to represent like this in energy band diagram point of view, because every time it takes time to represent like this. See, at 0 Kelvin, all valence electrons, that means for every silicon we have 4 valence electrons. All these electrons are under covalent bond. Under covalent bond, all these electrons. Similarly, now see, this covalent bond, this is our covalent bond. So this covalent bond is, I am representing like this. This is the covalent bond representation in energy band diagram. Yeah. So this is the covalent bond here. Same way, we have multiple covalent bonds. Now this is the covalent bond. Covalent bond. So covalent bond. So at 0 Kelvin, this is the way of representing the energy band diagram of a semiconductor. And this lower 4n energy levels are called valency band. Lower 4n energy levels are called valency band. Why? Because whatever the valency electrons here we have, these valency electrons are represented in this band. That's why it is called valency band. Okay. Now, I am going to increasing temperature up to room temperature. Now my temperature is 300 Kelvin. This is at 0 Kelvin, sir. And you observed at 0 Kelvin your this is the representation of your semiconductor. So that is at 0 Kelvin. So in 0 Kelvin you observed no electron is available here. That means no free electron is available. That means all electrons. See, this is the way of at 0 Kelvin your semiconductor is like this. So covalent bond, covalent bond, covalent bond. Like this. This is at 0 Kelvin. And this is valency band. You are saying this is the maximum energy level of valency band, EV. Now here let us, I am taking the temperature, room temperature 300 Kelvin. So 300 Kelvin temperature I am going to be applying here. So at 300 Kelvin what I am expecting is whatever the covalent bond here, that covalent bond is breaking and this electron is coming out of that. Okay, this electron is coming out of that covalent bond. So here now that means the same way here I am going to be representing in energy band. So this covalent bond is breaking. Now this electron is moving from valency band to here. Now you can call this electron is a free electron. Free electron. That means now this electron is not under the influence of any atom. It can move anyway, any direction freely. It is not under the influence of any atom. So that is free electron. Now this free electron is responsible for conduction. That's why this is called upper 4n energy states or levels are called conduction band. So that is the reason we called lower energy states are called valency band, upper energy states are called conduction band. And this is the minimum energy level of a conduction band. We represent that minimum energy level of conduction band is by EC. The minimum energy level of conduction band is represented by EC and maximum energy level of valency band by EV. So at 300 Kelvin this is the situation. Now see, at 0 Kelvin this is the case. Now at 300, so this is the case. EC, this is our EC, EV. So this is a 300 Kelvin we are taking. So this is the filled, these are the covalent bonds. Now these are the covalent bonds broken. Now electron is moving from this covalent bond to this one. That means it is free electron, we call it. So electron is moving from valency band to conduction band, free electron. So this is valency band, it is conduction band. So electron is moving from valency band to conduction band. Now this vacant position of electron in valency band is represented by the called by the term hole. Hole also provides conduction in electronics. So far you studied current is in the direction opposite to the movement of the electron, and most of you are thinking about electrons only provide the conduction. But in our electronics conduction is due to both electrons and holes. Okay, how hole is providing conduction? Physically hole is not moving, but appearance is hole is moving. Seems to be appearance is hole is moving. We feel that hole is moving, but physically hole is not moving, only electron is moving. Okay, even though hole provide conduction. How it provide conduction? Okay, while discussing about current densities there, I will show how hole provide conduction. Okay, now so these are the free electrons. These free electrons are responsible for conduction. That's why we called it as, now it behaves like a conductor. And here at this case, at 0 Kelvin, no hole is available and no electron is also available, no free electron also available in conduction band. That's why we called it as insulator. We called it as insulator. And here at 300 Kelvin, free electrons are available in conduction band and holes are available in valency band. Due to this and due to this, it provides conduction to us. That's why here it behaves as a conductor. And one more important thing, sir. For example, you got free electrons here, no hole. Then also semiconductor behaves like a conductor. Next possibility, no free electron is available, only holes are available in valency band. Only holes are available in valency band. Then also at that time also it behaves like a conductor. Okay, and in this case you need to identify one thing. Here number of electrons and number of holes both are equal. Someone may ask one thing, sir, if I am increasing temperature up to 400 Kelvin, what happens? What happens? More covalent bonds will break. More electrons you get in conduction band. More holes you get in valency band. Okay, just we go to that case also. Now let us, I am going to increasing temperature up to 400 Kelvin. This is EV 400 Kelvin. Previously at 300 Kelvin itself, this process was done. This breaking of first level of covalent bonds which are close to valency band was completed. Now next level at 400 Kelvin, additional covalent bonds are breaking. This is breaking. This one. That's it. So more covalent bonds are breaking like this. More, if you are going to increasing the temperature, more covalent bonds will break. Okay, and in this case, number of electrons is equal to number of holes. Okay, frequently you are getting some questions on this. The first question is, at 0 Kelvin, valency band is completely filled and conduction band is completely empty or vacant. That is the first important point you need to be considered. At 0 Kelvin, valency band is completely filled and conduction band is completely vacant. At 300 Kelvin, some covalent bonds are breaking. Due to breaking of these covalent bonds, electrons are moving from valency band to conduction band. See here actually what happens is, you mentioned this is energy gap Eg. Energy gap Eg. You can write that energy gap Eg is equal to Ec minus Ev. Okay. In case of conductors, it is approximately 0 electron volt in case of conductors. For conductors, and approximately 1 electron volt for semiconductors, and approximately or greater than or equal to 5 electron volt for insulators. Okay, so you can expect some questions on this. They will give approximate energy gap. Energy gap of a material is 0.97. How it behaves? So 0.97 is close to 1 electron volt. So it behaves like a semiconductor. Okay, energy gap is approximately 0.1 electron volt. Now identify the material. So it is a conductor because it is close to 0 electron volts. So energy gap of a semiconductor is energy gap of a material is 5.2 electron volts. So it is an insulator. Okay, based on that value also you can identify the type of material. And one more important thing, you may ask one thing, sir, you given some material and its energy gap is constant. Is it possible to change the energy gap of that material? Yes, it is possible, because energy gap is a function of temperature. If temperature changes, automatically energy gap also changes. If temperature changes, automatically energy gap also changes. Okay, so energy gap is a function of temperature and how it is changing. We discuss about this one in intrinsic and extrinsic semiconductors. We have another topic that is there, we discuss about that. Okay, now see, so here next, here, so temperature we increase it from 300 Kelvin to 400 Kelvin. Once temperature is increased from 300 to 400, more number of electrons are available, more number of holes are available. Anyway, it behaves like a conductor and its conductivity is increased. So this is called, this is our intrinsic semiconductor, what we have. In intrinsic semiconductor, these are the cases takes place. Already we mentioned, at low temperature semiconductor behaves like an insulator. See this, at 0 Kelvin semiconductor behaves like an insulator. It is because of no charge carriers, no free electrons in conduction band, and no holes in valency band. Because of this, at 0 Kelvin semiconductor behaves like an insulator. Next point, at room temperature, few covalent bonds in valency band are, few of the covalent bonds in a material or semiconductor are breaking. Now electron hole pair is generated. By breaking this covalent bond, one electron is generated as well as one hole is generated. Now electron hole pair is generated. Now due to that electron and hole pair provide conduction to you. That's why it behaves like a conductor. Okay, if they ask the question on how at low temperature semiconductor behaves like an insulator and at high temperature how it acts as a conductor, now you can write this is the solution. Okay, now if you explain that with energy band diagram, that is very useful, you get full marks. Okay, and in gate point of view you get these things in a statement, and in IES point of view there is a chance of asking questions. Okay, show how intrinsic and extrinsic semiconductors behaves like insulators at 0 Kelvin and conductors at room temperature. Okay, in that case, okay, you have to explain that by using energy band diagram. Okay, so you can use this part of the energy band diagram you can use for insulator. This is suitable for insulator. For N type you have to use another energy band diagram, and for P type semiconductor you have to use another energy band diagram. So that is the difference. Okay, and in detail about that one we discuss later in after intrinsic and extrinsic semiconductors. So this is the energy band, already we completed this. Okay, so upper 4 energy states, lower 4 energy states, and this is the energy gap Eg. Say at 0 Kelvin, this is the way of representing two-dimensional silicon, and this is its energy band diagram, respective energy band diagram. Next one is now. So our intention, see, once the temperature is increasing by breaking covalent bond, electron is moving from valency band to conduction band. Here our intention is to know about, to classify the direct and indirect semiconductors. Direct and indirect semiconductor. See, so just before we drawn the energy band diagram like this, we called it EC and it is a EV. Okay, if you take the energy band diagram of a complete silicon crystal, let us take this is a silicon crystal. This is a silicon crystal. If you draw the energy band diagram of this complete silicon crystal, it is not like this. Okay, why? Because let us, this is the same material, these are the silicon atoms. Just a minute, I will go back and I will show that one in a diagram. Yeah, see this in this diagram, if you observe, for this silicon, this side, this side, this side and this side, all the directions, number of silicon atoms are equal. But if you take this side, number of atoms are different, this side number of atoms are equal. Okay, but this side it is different, it is this side, this is different. And at the edges, these silicon atoms are not forming covalent bond in this side. You can take any material, because once you have a material you need to break it at one edge. Definitely you need to cut it at one edge, you need to cut it at that time. So definitely this type of problem you get. This type of bonds are called dangling bonds. And few more crystal effects takes place inside of the material, because it is a basically crystalline material. Due to all these things, the energy levels are not equal throughout the material, so they are changing like this. The EC and EV are changing like this. If it is EC and it is EV. Okay, now I am representing the energy levels are like this. So EC, EV, like this. Let us EC and it is EV. Okay. Now here let us covalent bonds are broken. Few covalent bonds were broken here. Just assume. Okay, 300 Kelvin I am representing temperature. Now this is the free electron and another free electron and another free electron. So we have total 3 free electrons and available energy states are 4n energy states. Okay, now only 3 electrons are available. 3 free electrons are available. Now these 3 electrons occupy any energy level which is available. Any energy level it can occupy. And that too, these are free electrons. Let us, here is one defined energy level. Here is one energy level. Here these 2 electrons try to occupy the same energy level. These 2 electrons are try to occupying same energy level. Once both are try to occupy the same energy level, what happens is collision takes place. Now during that collision, one electron will win the race and it will stay there, it will occupy that, and another electron which will lose, they will return back. That means they will fall. So this electron is staying here. Let us, it was win and it is lose, and this electron is going to occupy this energy level, and the electron second one which will lose is fall, return back to this and occupy the covalent bond, and it will occupy the, again it is forming a covalent bond here. Now the way how this electron is falling from conduction band to valency band, that is the my point now. How electron falling from valency band to conduction band. Here I am going to defining that in a case. Let us consider, take it as energy on this axis, and on this axis I am going to defining another parameter called K. We call it K is propagation constant. K is propagation constant. Propagation constant. Propagation constant K is. Okay, it explains about how movement of the carrier takes place in a material, how carriers are propagating in a semiconductor. Okay, in this case, two possibilities. First possibility is, let us electron is here, and in this case, you observed or not, this is the minimum energy level of valency band EV, sorry, conduction band EC, and this is the maximum energy level of valency band EV. Both are taken place at same K value. At the same K value, let us take K dash. Its minimum energy is at K dash, its maximum energy also at K dash. That is one possibility. And another possibility is, somewhere here electron is try to fall from this point to valency band. In that case, electron has, okay, let us take this point. Electron has to move from that point to some closest point, and from there it has to fall. That means here is energy K1 and here it is energy K2. There is a change in propagation constant. These are the two cases. Okay, now we go in detail about these two cases. In either both the case, once electron falling from higher energy level to lower energy level, once electron falling from higher energy level to, see, this is the case, here it is energy, here it is K value. So these are the two possibilities. This is the first possibility and this is the second possibility. Both are at a different K value. Here is let us take K1, it is K2. Here it is at K dash. Now this is EC because it is a conduction band, it is a valency band, it is maximum energy level of valency band EV. Same way here, it is the maximum energy level of valency band EV, it is the minimum energy level of conduction band EC. Once electron try to fall from this conduction band to this conduction band to valency band, electron falling like this, both are at same K value. Now the difference of energy will come out in the form of light. In this case, same way, electron is here. Now this electron try to fall from conduction band to valency band. Now this is the possibility and both are at different K value. In that case, first electron is moving to a temporary energy level ET, then from that point to it is falling to valency band. In this case, the difference of energy will come out in the form of heat or temperature. This type of semiconductors are called direct semiconductors. And this type of semiconductors are called indirect semiconductors. Or you can call it as a direct band gap semiconductor and this is indirect band gap semiconductor. Here the result is once electron falling from conduction band to valency band, only difference of energy is taken place, no change in the K value, propagation constant. Once propagation constant is not changing, momentum also not changing, because momentum and propagation constant both are directly proportional. Okay, so no change in the momentum of the charge carrier. Because of that, the difference of energy will come out in the form of a light. Here, once electron moving from conduction band to temporary energy level, here K value is changing. That means propagation constant is changing. Once propagation constant is changing, momentum of the electron also changing. So once momentum is changing, the difference of energy will come out in the form of heat or temperature. This is indirect semiconductor. The example for direct semiconductor is gallium arsenide, gallium phosphide, indium arsenide, indium phosphide. All this comes under direct band gap semiconductors. And here example for this one is silicon, is the indirect band gap semiconductor. See, already while defining the compound semiconductors, there we represented gallium arsenide and gallium phosphide are used to design LED, manufacturing of LED. Manufacturing of LED. LED is a light emitting diode. It is emitting light. That means output is a light. See, because of this reason, you are getting at output light. Okay, in this, your processor, what we have, what are the microprocessor you have? Your processor is designed by semiconductor, silicon. Okay, while operating your processor, it is going to be heating up your mobile. Once you are using your mobile for a long time and keeping your mobile charging for a long time, it will heat up. Okay, it is going to be heating. Because of that, this is the reason behind that. Okay, in this case, resultant output is a heat. Here it is a light. Okay, so to cool this processor, we are using different cooling solutions. We have use heat sink, fan. If you observe in your CPU backside, behind of your CPU backside, there you have a fan. That fan is for cooling of your processor. Upon your processor, let us take it is a processor. First level of cooling solution they will provide by pasting a white coating, white type of coolant material they will paste. Next level they will place heat sink upon this, and the next level they will keep fan upon this. This much levels of cooling solutions they are providing to provide cooling to your processor, because of this reason it is going to provide heat at outside. This is about direct semiconductor and indirect semiconductor, and the reason to use gallium arsenide, indium phosphide, gallium phosphide, all these materials in the designing of LEDs, lasers. Okay, this is it about this. Okay, so this is about your direct and indirect. So K is a propagation constant. It is a function of P. So K is a P by H bar. K is a P by H bar. See, and H bar is a, here H bar can be written as H by 2 pi, and here H is Planck's constant. It is Planck's constant. Its value we know that, and we discuss about in detail about this in before going to intrinsic and extrinsic. We discuss about in detail about this. And thanks for watching, and to subscribe Unacademy, just use my code VRAW10. Okay, and for notifications about my classes, just click on bell symbol if you like my classes. Okay, and there is a Telegram also is there. You can get the updates through Telegram also, and by clicking on this you can join the Telegram group. Okay, and I'm welcoming your valuable suggestions and valuable comments. Thank you very much.